Hi, in this video we will discuss about case study 2. This case study 2 is covering chapter 2 about statically indeterminate problem. In this case study 2, we will discuss this kind of problem. There are two cylindrical rods, one of them are steel and the other one is brass, are joined at C and restrained by rigid support at A and E for the loading shown, and knowing that E of the steel is 200 GPa and E of the brass is 105 GPa. We need to determine the reaction at A and E, and the deflection of point C. To answer this typical question, we must list all of the known given in the question. And the first one is E of the steel, which is 200 GPa, and then E of the brass, which is 105 GPa, and we have the dimension of the system. We need a strategy to solve this kind of problem. And the strategy that we use is by using a superposition and partition method. First of all, we can start to create the free body diagram for the superposition method of the system. We divide the superposition into two, where is the first one we assume that there is no fixing support at point E. There will be a deformation there. The second assumption is there will be a fixing support at point E, so it will give a reaction force at point E. This one. Then we will use the partition method to know the deformation occur in each part of the system. The partition is based on the change in external force, or changing in the cross-sectional area, or changing the material. For this problem, it can be divided into four different parts. The partition can be started from the left to right or the otherwise. In this example, we will start from the left to the right approach. And then, after we find the deformation for each partition, we add up all of the deformation to obtain the total deformation. Like this one, we have a deformation L. We add up the first partition, second partition, third partition, and fourth partition. Then we go through the partition method first. In this partition method, we must find the RA1 first to find the internal stress for the first partition. So, to find the RA1, we can use the sigma Fx equal to 0 to obtain the RA1, which is 100 kN. Then we go to the first partition. To obtain the P1, we can use the sigma Fx equal to 0 as well. So, the first partition for the P1 will having the same value as the RA1, which is 100 kN. So that's why we have 100 kN as the P1, and the L1 we got 180 mm from the dimension of the system. Then we go to the second partition. We have 100, which is RA1 minus by 60 kN, and we got 40 kN as the P2. And the L2 is 120 mm. That's come from the dimension of the system. It goes the same thing with the third partition. We have a P3 as 40 kN because there's no changing in the external force in the third partition, but there's only a changing in the material and the cross-sectional area. Then we go to the fourth partition. We got a 0 because the RA1 is 100 minus by 60 kN and minus by 40 kN. It will give us a 0 kN for the P4. Then, to find the total deformation occurred in the system, we add up all of the deformation for each part from the known data we obtained before, like the P1, L1, and the other. We just insert them in this equation. So, yeah, there will be the equation like this, where 100 kN times by 180, and this the cross-sectional area. And then This one is the type of uh, the material used, like steel, and this one is brass, and we will obtain the total deformation occurred is 0.145 millimeter. And then for the second sim, we have a free body diagram like this, where there will be a reaction at A2 and the reaction at E. There's no external force acted in the system, so we can use the sigma f is equal to 0, and we can equalize that the Ra2 is equal to Re. So for the deflection occur in the reaction, the air where there's a fixing support is P1 L1, P2 L2 only, because there's only two internal stress occur in the system, and only one part where the area is changing, and also the material is changing. So we will get this one where the Ra, which is P1, and Ra for the P2, and the length is different here. 180 is 120, we obtain 300, and there is changing in material 200 and 105 GPa. So we will obtain the deflection where the fixing support is 3.89 times 10 to minus 9 Re. Then after obtaining the TL and DR, we back to the superposition method that we have made before. We obtain the TL and DR, and we need to equalize them to find the reaction force at E. And then after equalizing them, we will obtain that the Re is equal to 37.27 kilonewton, and it's same with the Ra2. To find the Ra, we can't not use the Ra1 or A2 directly, but we need to add up them because this one is superposition method. So we will obtain this one where we obtain the Ra at this point. So we'll add up them, Ra1, Ra2, and the Ra is minus 100 kilonewton because this one is going to the left, and the Ra2 is 37.27 because it goes to the right. And we obtain the Ra equal to minus 62.73 kilonewton negative, and we have the Ra is going to the left. And then we go to the next question, where it is asking to find the deflection at point C. The first thing to do is create the partition method from point A to C. So there will be only two partition because there is only one times changing in the external force. So we have only P1 and P2. Then for the P1, we can find the internal force by using the sigma Fx equal to 0, and so the P1 will equal to Ra. And for the second partition, it is similar because it's using Ra minus by 60, and we got the P2. As shown in this equation, we will obtain a deflection at point C is 46.5 micrometer.